Okay, so now it's time. Shall we start?
Okay, yeah, perfect.
Okay, so welcome everybody. It's our pleasure today to hear Victor Roca and Lucio. I hope I pronounce your name more or less correctly. And he's
It's
going to
okay.
talk
Yeah.
about, okay?
Yeah.
And he's going to talk about hierarchy theory in positive characteristic. So it's yours.
Okay, well, thank you for the invitation. So there is a lot of homotopy theory within what I'm gonna explain, but I realize that this is an algebra seminar, so I'll try to keep it mostly under the rug. But if you have questions or any doubt or things like that, please interrupt me and ask questions. So wait, there is okay. Yeah, okay. So I'm gonna I can hear myself. Sorry. Sorry. Uh, okay, maybe if I do this. Can you hear me?
Yes, we can hear you.
Okay. So I'm gonna start talking about the motivation behind Lie theory and what it is, and also behind higher Lie theory. Because, well, the title might seem a bit cryptic as it is now. So, okay, let me start with some motivation. And also, let me give a brief overview of what can be called higher Lie theory. And so, all of this, as I said, comes from kind of homotopical motivations, but I will try to focus on the algebraic aspects because this is an algebra seminar. And so, I think, well, as I said, uh, if you have questions, please do so. So, to begin with, Lie algebras, they appear in correspondence with groups. So for the moment, let me choose K a field of characteristic 0. And let me remind you how one can get this classical correspondence between Lie algebras and groups. So in the algebraic setting, you can do that with an underlying topology and get Lie groups. But in the algebraic setting, let me choose an important Lie algebra, G, uh, maybe finite dimensional, and for the moment, maybe K can be Q. The way one can get a group out of this Lie algebra is via the following construction. So you take G as the same underlying set. So, and now you're going to endow it with a universal group law, which is the Baker-Campbell-Hausdorff group law. And so this group law is given by, as I said, a universal formula. And so let me first write, well, let me write the first terms of this formula. So for any two elements in G, you take first their sum, then you take 1/2 of their bracket, and then you take a 12 of an iterated bracket of X and Y. And then, well, and then the formula goes on forever, having higher and higher brackets, meaning brackets which are iterated brackets of iterated brackets of iterated brackets. And you have 1 over something factorial coefficients. So this formula, well, it's only defined in characteristic 0 in general, and it's an infinite sum. And that's why we chose G to be nilpotent to begin with, so that at some point the iterated brackets become null, and so this sum becomes finite, and it's well defined. And then what I claim is that this is a classical construction that gives you out of a nilpotent algebra a group. So you can forget the title of this talk. My goal is really going to be how to sketch a possible generalization of this construction in characteristic P, which omits these 1 over factorial coefficients. But in order to do so, I'll have to take a very long detour through higher Lie theory and then higher Lie theory positive characteristic, and then what should be the analogues of what I'm explaining right now. So I'll come back to this picture a bit later. Now let me give an idea and some motivation for higher Lie theory. Okay. So the main motivation really comes from deformation theory. You have this equivalent. So deformation theory seeks to deform, say, a type of structure on an object. You have a well-defined definition of what a deformation problem is, given by Lurie-Pridham, and then you have an equivalence between these deformation problems and some type of Lie algebras. I'm not going to get into the very details of all of these. My point is that because of of this equivalence between some type of Lie algebras and these deformation problems, which is an equivalence at the homotopical level, you need to generalize this classical integration procedure to a homotopical level as well. So, and that's what I'm going to try to sketch now. So you can sum up higher Lie theory to some extent as the quest for a functor which goes now from differential graded Lie algebras to simplicial sets and, well, more concretely, so Kan complexes. And here it's really the image you should have is that what we want to get is an infinity groupoid. And I'll come back to this picture again and explain a bit more in detail why it's really an infinity groupoid in some precise algebraic sense. But so why do we want that? And let me explain what this involves. So first we have differential graded Lie algebras, which are chain complexes endowed with a compatible Lie bracket with the appropriate sign rules. And we end up, instead of sets, or rather groups, we end up in what should be thought as groups up to homotopy. Okay. And so this integration functor, as I said, needs to, well, as I didn't say, needs to satisfy some elemental properties. In particular, it needs to be well behaved in terms of homotopy theory, meaning it respects quasi-isomorphisms, it sends them to weak equivalences, and then some other important properties, which I'm not going to get into. Now, a first construction of such an integration functor was given by Inich, but it was too big from an algebraic point of view. So it gave you something here which had the right homotopy groups, but as a simplicial set, it was too big algebraically. And a refined version of such an integration functor, so let me... So a refined version was constructed by Getzler. I think this is 2001 and this is 2009. Okay. And so this refined construction had the same homotopy groups as the one before, but it was refined algebraically in the following sense. So now if we take G an nilpotent Lie algebra, which can be seen as a DG Lie algebra in degree 0, concentrated in degree 0. So if you take this classical Lie algebra, which is nilpotent, and you integrate it in the sense of higher Lie theory, what you get is the classifying space so the classifying simplicial set of the group X of G. So using Gessler functor, we really do get as a generalization of the classical procedure of Lie theory of integrating an nilpotent Lie algebra into a group. And now let me perhaps explain in which sense these simplicial sets in general can be considered as really groups up to homotopy. So infinity-groupoids in the sense that they are groups, but only up to higher homotopies. Okay, so in order to do so, perhaps I want to slightly change the setting I'm working. So in fact, I've lied a bit because Gessler functor is defined for something called L-infinity-algebras, which I'm going to define now, which are another version of differential graded Lie algebras in some sense. What I mean by this is that combinatorially, algebraically, they are different data, but their homotopy theory is equivalent to that of differential graded Lie algebras. And that's why it really doesn't matter that much, at least at the homotopical level, whether you choose one or the other. And here by homotopical level, what I really mean is that you formally invert all quasi-isomorphisms of structures in the same way that you do that to get the derived category of a ring, for instance. But here it's with algebraic structures up to quasi-isomorphism. So now let me really say what the differential graded Lie algebra is. So a chain complex G plus a collection of operations Ln, which are symmetric for n bigger or equal to 2. And so the idea here is, why is it an L infinity, also called a Lie algebra up to homotopy? Well, because the L2 bracket satisfies the Jacobi relation only up to higher homotopies. And these higher homotopies are given by L3, L4, and so on. Okay, so you have an infinite amount of such operations which take n inputs, and well, Ln takes n inputs and gives you one output. And notice that, well, here I said they are symmetric because there is a shift somewhere happening. And so something with chain complexes, if you shift something antisymmetric, like a usual Lie bracket, you get something symmetric. But let's not get too much into that. Just remember that the L2 has the same antisymmetric property as a Lie bracket, a usual Lie bracket, but it only satisfies Jacobi up to these higher homotopies. And why working in this setting is important? Well, because in this setting, it's a more relaxed version of what a chain complex with a Lie structure is, but relaxing and adding all these combinatorial operations, what it allows for somehow simpler formulas and to really work out what these simplicial sets look like. So now let me mention the following work. So Robert Nicou and Valette, 2020, they gave another description of Gessler functor, which was very much non-explicit in general. And they gave a much more explicit version, well, description of the same functor. And in particular, what was interesting was the following result. So perhaps let me remind briefly. So this is a simplicial set, but we want it to be a Kant complex. So let remind in general the reader the definition, the listener, the definition of what a Kant complex is. So a simplicial set is a Kant complex if for any horn inside the simplicial set there exists a filling. So a filling meaning you can extend this horn to the full simplex. An example of this is that, for instance, if you give yourself, this is the 2-1 horn, so if you map this into this simplicial set, there needs to exist an extension to the full 2 simplex, like this. So in the usual definition of a Kant complex, you only require that these fillings exist without asking for anything more. So Kant complexes, they are a model for the homotopy theory of topological spaces, but they are sometimes also called infinity-groupoids, but they are not so much algebraic. They are not so much algebraic in the sense that they're really groups up to homotopy. But here what Robert Nicot and Valette proved is that, in fact, for the simplicial set Rg, where G is an L-infinity algebra, you have that these fillings not only exist, but actually can be characterized. So the set of all fillings is in correspondence with the degree n elements in G. And this correspondence is given by explicit formulas. So instead of having something that satisfies a property, now this is extra structure. And it is in this sense that I mean that it's really a group up to homotopy. This simplicial set is really endowed with a structure which is given by all these horn fillers, which are given by explicit formulas. And these formulas involve, well, they involve these ln operations and compositions of thereof. And so when the interesting thing now is that when you take G again to be a nilpotent Lie algebra in the classical sense, and then you take the 2-1 horn filler, so here you're going to do this around the point 0, which is always a 0 simplex in G. So now if you take degree 1 elements, and this is because of the shift that I mentioned before, but you just imagine you're working with the classical Lie algebra. Now, the filling here to extend to the 2 simplex is really going to be determined when you put 0 in the middle. It's going to be determined by a unique element here. So we had x and y, and then we have an element here, and this element is precisely the BCH of x and y. And so that's how you recover the classical Baker-Campbell-Hausdorff formula from these horn fillers which exist for any n and any k. And so that's why they call these higher fillers, they call them higher Baker-Campbell-Hausdorff formulas. So these, they give higher Baker-Campbell formulas. Okay. So so we're good. Okay. Okay, good. So now I want to briefly finish by saying that, well, these formulas that give these higher fillers, they are always infinite sums. So I also worked a bit in the characteristic 0 setting, and what I did in my thesis was to generalize this integration theory to something called curved L-infinity-algebras. So it's not very important what they are, but the only thing that I want to mention about this is that usually, because you always need to make sense of infinite sums in the theory, you need either to ask for some nilpotency or to complete with respect to some filtration. But it turns out that there is somehow a more conceptual way to deal with this, and it's to work with so-called absolute structures. So you basically work with absolute L-infinity algebras here. And there is a precise definition that I'm not going to give, but basically keep in mind that these are objects which have well-defined images for any infinite sum by definition. So it's a way to get rid of infinite sums. Well, at least not really get rid of, but at least make sense of them without asking nilpotency or completeness conditions. It's a bit more general. So I mentioned this because now I'm gonna work with these absolute structures as well, and there will be infinite sums, and in this context, they can be makes one can make sense of them in more generally than just in the nilpotent or complete case. Okay, good. So this is Lie theory and higher Lie theory in characteristic 0. And now what I want is to somehow talk about higher Lie theory in characteristic P. And so let me put a disclaimer. So higher Lie theory is also interesting in characteristic P, and it relates a lot to deformation theory. But the path we're going to take and the end goal of the things that I want to explain is not so much about higher Lie theory. So if you don't care about homotopy theory, you should still be listening, I think, to what I'm going to say, because somehow generalizing higher Lie theory to positive characteristic is also a way to try to amend somehow the problems of classical Lie theory in positive characteristic. Let me somehow be more precise. So all these correspondences between Lie algebras and groups, they largely break down in positive characteristic. So uh, there is a correspondence called the Malchev correspondence between uniquely divisible nilpotent abstract groups and nilpotent Lie algebras over Q. This correspondence breaks down in characteristic P, at least to the extent of which the Baker-Campbell-Hausdorff formula is no longer defined. And that's called, this partial correspondence is called the Lazar correspondence. But many things like correspondences with algebraic groups and so forth, they all break down when you work with Lie algebras in characteristic P. But now the main idea of what I'm going to explain is that what you can do is you can try to generalize, instead of generalizing Lie theory to positive characteristic, you can try generalizing higher Lie theory to positive characteristic, and then try to find an analog of classical Lie theory within this more general theory, which is better behaved than actual Lie algebras. So this is really what I'm going to try to explain in the remaining time that I have. So recall I mentioned this orally, but there is an equivalence by Lurie and Pridham at the homotopical level between deformation problems, which can be make sense of in terms of formal moduli problems, and differential graded Lie algebras up to quasi-isomorphisms, which are equivalent, as I mentioned, to differential graded Lie algebras up to quasi-isomorphisms as well. So in some sense, we have higher Lie theory because this correspondence exists. Now, uh, from the point of view of homotopy theory, Lie algebras are no longer well behaved. Neither L-infinity algebras, in fact, are no longer well behaved in positive characteristic. So now this is only characteristic 0. So now let K be a field of any characteristic. There is an analog recently proven by Brantner-Mathew of the Lurie-Pridham theorem. So what they show is that in general, deformation problems in these more general contexts, they're equivalent to something that they call partition Lie algebras. And so these partition Lie algebras initially they were only defined at the derived level, so more concretely at the infinity categorical level. So you can think of this as somehow being defined only at the level of their derived category. At least that's to begin with what happened. But they still managed to establish this analog of the Lurie-Pridham theorem. Mathew. And then, well, later, Brantner Campos and Newton, and also it comes out of the Brantner, Campos, and Newton, they constructed what it's called point set models for these objects that only exist at the derived level. What I mean by this is basically they showed that certain algebraic structures localized at quasi-isomorphisms, they give you back the right homotopy theory. And so also a very specific choice of point set models comes also from the joint work with Le Grignot. But now the idea that I want you to keep is that there is a new type of algebraic structure that comes out of deformation theory in positive characteristic, and that it plays the role of Lie algebras. And what I want is to be very explicit from now on. And so if you want to forget about deformation theory and homotopy theory, you can. Let me first define what a partition L-infinity algebra is. So very explicitly, now G is again a chain complex, but it has even more structure than before. So it's endowed with a collection of operations, Ln, like this. So here, this is a tuple, an R+1 tuple of permutations in Sn. And so for any n bigger or equal to 2 and any tuple of permutations such that sigma I is different from sigma I plus 1, there is such an operation, again with n inputs, so it takes n inputs and gives you one output in G. And this structure satisfies quite complicated relations. So now I want to give an idea of what these relations mean, and then I'll write the first one. So what you can think about is the following. A Lie algebra is a very strict object. In characteristic 0, when we want to do higher Lie theory, say, you relax the Jacobi relation in the following sense. So you take a bracket which is antisymmetric, but only satisfies the Jacobi relation up to prescribed higher homotopies. Here, what you do is that the problem with characteristic P is precisely the antisymmetry. So what you do is that you relax both the Jacobi relation and the symmetry of the bracket up to homotopy. And so the homotopies for the symmetry of the bracket, they really they are given by precisely these higher operations labeled by tuples of permutations. And so let me write down the first relation that's satisfied in such an algebra. Okay, so here we have the initial bracket, the L2 operation. We compose it on the left with itself. This is the meaning of this. Okay. So this relationship is written without elements, but if you want, you can say that it's satisfied when you apply all these operations to a three tuple of elements in the partition L-infinity algebra. And so this thing has to be equal to this other thing. And here we have so we have the identity on the right, and then any permutation which is different from the identity on the left, and likewise, but with permutations on the right and the identity on the left. Also, I want to note that none of these operations are symmetric. They satisfy no symmetry, but if you permute the entries of your operation, you act on the right by the permutation of the entries, okay? So let me be not very explicit about this, but basically if you permit the entries, you have a sign and then you alter the label of your operation. This will appear somewhat hidden in the following, okay? But just keep that in mind. Okay, so let me first state the theorem quite vaguely. So there is an adjunction between simplicial sets and the absolute version, as I said, of partition L-infinity algebras. And here, well, where R is an integration functor. So because I didn't really specify what kind of properties it needs to satisfy, I will not get into the details. Just know that this integration procedure and how it relates to deformation problems and so on, it can be generalized to positive characteristic setting. Instead of working, well, with L-infinity algebras, now you work with this partition L-infinity algebras because they are the objects that encode deformation problems. So this exists, okay? And well, R satisfies some properties. There's also, let me mention it now. In characteristic 0, there's also a left adjoint, and it was used by Robert, Nicot, and Valette to construct rational homotopy models for spaces. If you know what that means, then, well, know that this can be also generalized to get p-adic models for spaces. But I will not talk more about this. So if you're interested, maybe ask at the end. But that's not the thing I want to focus. The thing I want to focus now is that now that we have this integration functor, what we can do is we can generalize this description. So here RG is again an algebraic Can complex. And so in particular, like in the characteristic 0 setting, these horn fillers in G, not only they exist, but their set can be characterized as the degree n elements, and this correspondence is given by explicit formulas. And so in particular now, as I said, the game is to try to do classical Lie theory with these objects. So in particular, well, what happens for the Horn filler, which gives you the classical Baker-Campbell-Hausdorff formula? Well, when you consider this Horn filler, what you get is, well, what I call the Horn filler formula, which is given as follows. So let me write it in full because I will give examples at the end. So, sorry, it's minus. So you take two elements in your partition L-infinity-algebra, and now the element that's spitting out as the filler, in the third side of the triangle is the element given by the following formula. So you take their sum. Now you take their first bracket, and now you have this L3 operation, which involves x, x, y. You have this, sorry, it's a minus, and it's a minus here as well, minus 3, 2, 2, 1, 3. Yes, okay. X, y. So you have 4 terms in x, x, y involving L3, and now you have 5 terms involving x, y, y. So trying not to make any mistake while I copy this. Okay. Plus, and now there's a plus. 32 and x 3. Almost there. Okay. X, y, y. So these are all the terms that appear involving L2 and L3. And then, well, then it's an infinite sum. So you get plus minus, then L3 composed with L2, some permutations, and then you're going to get some L4 and with some permutations and so on and so forth. So, of course, I just wanted to write the first terms, but then you get an infinite amount of terms as you go on. And, well, these terms are structural operations. The first thing to notice is that in this Horn-Filler formula, all the coefficients are plus minus 1. So there is no so meaning that this formula is defined in any characteristic. That's the first point that I wanted to make. Now, kind of anticipating the main theorem that I'm gonna write down in a moment. One thing that I want to also explain is that, well, now take G, which is 3 nilpotent. So what I mean by this is that all the compositions of L2 and L3, they all vanish. So you get only this formula, which stops here. Now, if G is 3 nilpotent, you can check by hand, in fact, and as an exercise, that this formula is associative precisely because of this relation. Why? Because if you do HH composed with itself on the left, you're going to get by bilinearity, you're going to get 10 terms which can be written as X, Y, and Z. Then you need to repermute them to make them in order by suitably acting the permutation on the labels. And then if you do HF compose itself on the right, you're going to get 8 terms, again, in terms of X, Y, and Z. And now what happens is that 4 cancel on each side, and the remaining 10 are equal precisely because of this relationship. So it's kind of a fun miracle, but you can check that it's associative, and you can also check that, in fact, HF defines a group law. You can also check this by hand. Indeed, if you set for any element the following formula, then you can check that it defines an inverse for any element. So the inverse is really given by minus x minus L2 of x, and then minus the sum of the L3 operations that are labeled by transpositions applied on xxx. So it's kind of a fun game to check this by hand. Now, the general theorem that I want to state is the following. And so also, okay, let me be a bit more precise here as well before I state the theorem. So this formula is well defined. It gives you the pi1 of the RG. So it gives you, it's a formula that always works because it's related to this horn filler. But now, within this higher Lie theorem characteristic P, what we want is to find the analog of the classical Lie theorem characteristic P. And so that's why we restrict now to objects which are in degree 1. So because there is a shift, you have to imagine that this is the analog of taking a differential graded Lie algebra concentrated in degree 0, which is precisely just a Lie algebra. Okay, so now let G be a nilpotent partition L-infinity algebra in degree 1. So concentrated in degree 1. So it's basically a vector space with certain operations. You have to, again, think that because of degree reasons, the only operations that will remain in this case of all these labels are the ones which are labeled by n+1 tuples. And these will be the remaining ones when G is in degree 1, okay? So you still have an infinite family of operations, but now you restrict the size of the tuples that label them, okay? So now the interesting thing about this situation is that there is always a restriction functor from these partition L-infinity algebras to classical L-infinity algebras. But what happens is that when you take such an object, the restriction of this object is precisely a nilpotent Lie algebra in the classical sense. So really, it's an nilpotent Lie algebra. And now what one can prove is the following. So first, there is an isomorphism between RG and the classifying space of G as a vector space endowed with the group law given by the horn filler formula. So in particular, this statement is that the Horn-Filter formula always defines a group law on the underlying vector space of something that's concentrated in degree 1, okay? And so the integration gives you back this classifying space, and because this guy is nilpotent, you get a nilpotent group. And secondly, if now this works in over any field. So now if K is a field of characteristic 0, then there exists an isomorphism between this underlying vector space with the group law given by the Horn-Filter formula, and the group that you get. So this is the exponential group of the restriction of G. So it's underlying nilpotently algebra. Okay. So this is very good. So we have this general theorem, which is proven by abstract homotopical methods. So as I said, you can check by hand the 3 nilpotent case, but in general, the way you prove that, oh, sorry, I misclicked. In general, the way you prove that this is a group, well, it's because it's a pi1 of something, right? And again, this isomorphism is really non-explicit. So in general, it exists because two things are homotopy equivalent. But so that's why somehow you have this general theory and then this general Horn-Filter formula, which because of this theorem, you can think of it as some kind of generalization of the Baker-Campbell-Hausdorff formula, which works in positive characteristic. But now what I want to end up is with some very explicit examples for very given groups, so very explicit groups, how you can get them as the integration of explicit partition L-infinity-algebras, which will be concentrated in degree 1, okay? So let me end with some concrete examples. Okay. So the first one is the following. So take G to be a dimension 3 vector space over K. And now we endow it with an L2 operation. It goes from a tensor product because it needs to be linear, but it's not necessarily symmetric, as I said. So here you have 3 elements. You also have 3 elements here. And what you send them is to 0, 0 minus alpha times beta prime. Okay. Well, you can check that. Okay, and then all other ln labeled are 0. Okay, so you only choose this L2 operation. So it's too nilpotent because any composition of itself with itself is 0. So in particular is associative. So notice that again in the relationship that I wrote, where is it? Yes, here. If these L3 operations are all 0, then basically this relation amounts to L2 being associative. So it is a partition L-infinity algebra in the sense that I wrote. Okay. So it's the relationships are satisfied. And now what you can check is that the group you get from the Horn-Filter formula here well, we only have the L2, so it's minus L2. You can check that this group is isomorphic to the group of upper triangular matrices with coefficients, wait, I think it's beta and then gamma here. So this is U3 of K, I think, if I'm not mistaken. So this is a nilpotent group, a nilpotent abstract group. And so you get this isomorphism between the group obtained by integrating this very simple partition Lie algebra and then this group. Notice that this example can be generalized and you can construct a similar partition L-infinity algebra in degree 1 with only L2 operations that integrates UN, so the n times n upper triangle matrices with 1 in diagonal. Okay. Now let me write another example, which is a bit more sophisticated. Okay. So, okay, before I write it, actually, let me just point out one last thing, is that there is a Lie model for this object, but not in characteristic 2, because you need a Lie bracket to construct it. And so if we go back to the Baker-Campbell-Hausdorff formula in the beginning, because you need a Lie bracket, you need these terms in the formula. So in particular, you need to be able to divide by 2. So that shows that this is an example which works for this partition and infinity algebras, but it doesn't in the Lazar correspondence. Okay, and with classical Lie algebras, you can't get this group in general. Okay, now let me write another explicit example. So now it's a model for Z over 4Z. So this is a very simple nilpotent P group, but still. So how do we get it as the image of a partition infinity algebra? Okay. So here you take F2 as a two-dimensional vector space over F2. So as a set, it's isomorphic to a Z4, but now the game is to recover the group law. So here again, we can obtain it only by taking L2 operations. So an element in F2 is going to be a tuple A and X. And so the L2 operation here is given by X times Y, 0. It's 2 nilpotent. Okay. And then ln whatever, they're all 0 here. And well, what you can check is that now and those F2 plus 2 with the group law, so sorry, yeah, so hf of ax y, sorry, by, this is given by, well, a plus b plus x times y, and then on the second variable it's x plus y. And this group law on F2 is in fact isomorphic to Z over Z. So what you get is that, I mean, you can check it. It's quite simple to convince yourself that this group law, it really gives back Z over 4Z. Okay. So now I want to end perhaps with a much more intricate example, I think. So it's a model for Z over 8Z. So here already, I think some interesting things start to happen. So one can take the F2, a three-dimensional vector space over F2. So that's in bijection with Z over 8Z, okay, as a set. And then now the question is there a partition L-infinity structure on this vector space seen as a partition L-infinity algebra concentrated in degree 1, such that when I apply the Hornfiller formula and obtain a group, do I get Z over 8Z, okay? And so you can define the L2 operation as follows. So now it goes from a 3 tuple, okay? So you take the second and then you multiply and put them in the first spot, and then you take the third and you multiply and put it in the second spot, okay? And then in the third you put 0. So its composition with itself is not 0, but then if you recompose it with itself afterwards, it's 0, okay? And because its composition with itself is non-zero, then we need some L3 operations as well, okay? So then one can define the following. So one can define so we define the following L3 bracket. So it's associated to this precise tuple, and it sends, so it has 3 inputs, and every input is a 3 tuple. So it associates to this the following 3 tuples. So you multiply the second of the first, and then the third of the second, and then the third of the third, and then you put 0 everywhere, okay? So it's very specific. Okay. And now what happens is, yeah, it's very surprising. So first, why is it a partition L-infinity algebra? Does it satisfy the relationship? So in fact, you can compute that, well, L2 composed with itself on the left. That's, let me cheat a bit, okay? So that's X2, Y3, Z3. Oh, and let me mention that this is, sorry, I should have said it before. So we said this particular L2, this particular L3 operation like this, but all the other L3s are 0, and all the other LNs are 0 as well, okay? So it has only a one L3 operation. So if we go back to the relation it needs to satisfy, okay? So it's this relation again. So we have this term, and then this sum only involves a particular element, okay? And this particular element, okay, sorry, I made a mistake. So the L2 compose 1 with L2 is not this, it's X3, Y3, 3, 0, 0. And then when you add it to L3 of, well, you need to, so these things, so this is identity sigma, okay, well, this sigma is the cycle. Now you can also rewrite it by permuting the entries as sigma minus 1, the identity. And because the cycles in S3 are inverse to one another, what you get is, well, let me write it like this, sigma of, and then the things permuted, okay, so I have to think, but maybe it's something like this. Maybe there's a small mistake, but still what you get is the following. So you get, again, 3, 3, Z2, 0, 0. So on the left side of the equation, you get 2 times the same term, which modulo 2 is 0. And so that's left side. And then when you compose L2, L2 with itself, then you get this x2, y3, z3, 0, 0. And then this L3 identity sigma, then it's also x2, y3, z3. So again, all of this is 0 mod 2. So we have 0 on both sides of the relation, so it does satisfy the relation, and it is indeed a partition L-infinity algebra in degree 1. And now if you compute the Horn-Filler formula, so let me write it like this. For alpha and beta, the terms that are going to appear are going to be alpha, beta, L2 identity of alpha, beta. So here we are mod 2, so the signs don't matter, okay? And then we have identity 2, 3, 1 of alpha, alpha, beta, plus identity 2, 3, 1 of beta, alpha, beta, okay? And the other terms are 0 because the other L3 operations are 0. So this is the Horn-Filler formula in this case. And now the group law that it defines, let me write it down, and then I'll be finished. So for 2, 3 tuples, what you get is on the first coordinate, you add them, plus you take the product of the second, that's the L2 contribution, and then the contribution of the L3s is x2, x3, y3, plus y2, x3, y3. That's on the first coordinate, and then on the second, it's x2, y2, plus x3, y3, and then on the last one, it's just x3 plus y3, okay? And now, finally, you can check that the following bijection is in fact a group isomorphism. So you send 1, 0, 0 to mod 4, then you send 1, 0, 0 mod 2, and then you send 0, 0, 1 to 1. This set bijection, when you endow the left side with this group law, it becomes a group isomorphism. So that's how you get Z over 8Z. And there is also an analogous thing involving Z over 9Z. Okay, so that was to show that in fact you can get very specific and very explicit with these algebras as well. So, and to finish, yeah, let me mention that although the main theorem it was in my paper, these examples are they belong to a joint work with Geoffroy Well. Okay, so thanks a lot for your attention, and please, if you have any question, tell me.
Thank you very much. Are there any questions? I have a few questions, if you don't mind. So you can do it for z over 4 and z over 8 and z over 9, if I understand well.
Yeah.
Do we have other examples?
Well, I mean, what we're working on is to try to generalize the Lazar correspondence into a correspondence between these precise partition, well, these things in degree 1 and then nilpotent p groups in general. So, but yeah, the abstract, so a theorem that would establish such an abstract correspondence, it would be non-constructive. So in fact, constructing higher examples then becomes even, I mean, more and more complicated because you need bigger and bigger operations, and you need to be able to check if they satisfy the relationships or not. So, okay.
Okay. I can imagine it's not so easy to prove that it satisfies the relations.
No,
And
yeah,
you, yes, and you obtain also unipotent matrices uh,
yeah,
before. In any characteristic, or I don't remember.
yeah. In any, all of this is in any characteristic. Yeah.
Okay. Uh, so is there an operand for partition L-infinity-algebras, or
Yes,
is it
yes.
more complicated?
No. Yeah, there is an operand. So not at the homotopical level, but at the so for the models we're working with, yeah, they are algebras over a certain operand. Yes.
Okay, and is it a complicated operand? Can you describe it with a combinatorial structure, or is it
So,
really very complicated?
well, I don't know if you're familiar with, but there is this Baratekol's operand. Well, the chain complex version of it, which was introduced by Berger and Fraisse. So you have, this is an operand. So in particular, you can take the linear dual of this.
Hmm?
It's a coparad, and now you can apply something called the cobar construction. So this is the kind of objects you're
Okay,
considering. So this would be the
so it's
operand that you end up considering.
okay. So it's rather complicated.
Yes, well, that, and also the reason why the relationships are so complicated is because they stem from the compositions inside these coparad, and the compositions are very hard to compute in general.
Okay. Uh, How far it depends on the characteristic.
Hmm?
How far it depends on the characteristic. Is it very different in characteristics 2 and 3 and 5 and so on?
Well, the interesting thing is that this integration theory and the formula, they work at, well, it's not proven, but they should in principle work over Z even. So,
Okay.
but then what's funny is that, well, this example of unipotent matrices, it works in general for any K, but when you construct models for Z over 8Z, well, this uses a lot in order to show that it satisfies the relationship that, well, 2 is 0 mod 2.
Yes, I can understand.
So
Okay.
then for the examples, it's characteristic dependent, I would say, yeah.
Okay. So thank you very much for your answer. Are there any questions? It does not seem so. So thank you again for your talk. Thank you very much.
Yeah, thank you for the invitation.